Hello students, welcome to video lesson 8.1. We're going to start chapter 8 today, and we're going to eventually get to trigonometry. It's all going to be about triangles. The first number of sections, in fact maybe all the sections we're going to do are going to be specifically about right triangles, so sort of get back in that mode of all of these triangles are right triangles for at least today and our next video as well. And we're going to start with something that I think we've all seen before and we're all relatively comfortable with, but we're going to extend it a little bit today, okay? And that is the Pythagorean Theorem. So we have been introduced before to the Pythagorean Theorem to find missing sides of a right triangle, right? So this would be the type of thing I'm asking you to do. Find the length of this side that's labeled x. We would use our Pythagorean Theorem. A squared plus b squared is equal to c squared. Remember that the hypotenuse across from the 90-degree angle is always the c value by itself on the other side of those of that equal sign. So of course this would become 25 plus 144. 25 plus 144 is 169 is equal to x squared. And then we can solve that by unsquaring or square rooting both sides, and we end up at 13. Now remember, when we square root, we always have a positive negative option, but in geometry class, because we're talking about lengths of things, we do not worry about the negative version. We just take the positive answer, okay? So the Pythagorean Theorem, just as a little refresher, a squared plus b squared equals c squared. We can write that down if we want to. It is in your book. It is a theorem, the first theorem of chapter 8, the Pythagorean Theorem. There it is. You can look at it there if you want. Something else in terms of vocabulary that we'll need for our practice problems is your book will talk about Pythagorean triples. Okay, and we may have talked about these back in Algebra 1, but if we didn't, I'll just go over it here. Again, a Pythagorean triple is a set of numbers that are not decimals that fit in the Pythagorean theorem, okay, that satisfy the idea that a squared plus b squared is equal to c squared. So the most common and the most basic is 3, 4, 5, because 3 squared plus 4 squared is equal to 5 squared, right? Another example, 5, 12, 13, 8, 15, 17, and so on. You can look up lists. There are infinitely many Pythagorean triples. The reason that there are infinitely many is because anytime you have a Pythagorean triple, every multiple of those numbers is also a triple. So for example, 3, 4, 5 can turn into 6, 8, 10 if we just double all those numbers, or it could turn into 9, 12, 15 if we multiply each of those numbers by 3, multiply each of them by 4, and so on, we get other Pythagorean triples. So if you're asked to determine if a set of 3 numbers is a Pythagorean triple, you can simply plug them into the Pythagorean theorem and see, does it work? Is it true? For example, is 8 squared plus 13 squared equal to 15 squared? Well, 8 squared is 64, 13 squared is 169, and 15 squared is 225. So is that true? Is 64 plus 169 equal to 225? Well, it's kind of close, but no, it's actually 233, I believe. Yeah, 233. So this is not a Pythagorean triple. 8, 13, 15 is not a Pythagorean triple because it doesn't fit. This is not a true statement, so it doesn't fit the Pythagorean theorem. Okay, so Pythagorean triples in your homework will just be yes, no questions. Is this one, is it not? Make sure that you can prove it to me by the Pythagorean theorem, okay? Another thing that we can do and that we have done before with the Pythagorean theorem is find the length of a leg of the triangle instead of the hypotenuse. Just as a reminder, when you plug values in, if you know the length of the hypotenuse, that has to be the c value, has to go in the c value. And then we have our x being added to 64, right? X squared plus 64, so we would just minus the 64. x squared would then be equal to, what? 336. And then we would square root each of those. X would equal whatever the square root of 336 is. I don't know it off the top of my head, but it might be, I don't know. I think it will come up as a decimal in our calculator, which sort of leads me to another important thing to say at the beginning of our extension of the Pythagorean theorem. Your book is going to talk a lot about simplest radical form. This is something that we talked about back in Algebra 1, but it's not something I'm going to require you to do right now, okay? So expressing your answer in simplest radical form, you can always sort of disregard this sentence in the directions, okay? You do not have to do this. You will never have to do it. You can always answer as a decimal rounded off to maybe 2 decimal places if you need to on a quiz or test or in your homework, okay? If you want extra credit, you can answer things in simplest radical form. Now, what that means is when I end up with the square root of 336, if it comes up as a decimal on my calculator, I have to do the split thing, okay? I have to find, okay, what's a value that goes into 336 that I can square root very nicely and easily, okay? That basically just involves trying different things. 336 maybe divided by 36. That doesn't quite work. Divided by 9 doesn't quite work. Divided by 4, divided by 16 is going to work, okay? Divided by 16. So I can split the 336 into 16 times 21. I can square root each of those, and I end up with 4 radical 21, and that would be the simplest radical form because 21 cannot get split up at all. So this is going to be extra credit if you ever do this on a quiz or test, and you can go ahead and practice it in your homework. I might give a little extra credit for your homework, but not a ton, okay? So answer as decimals. It will be extra credit on quizzes or tests to do the splitting of our square roots, okay? Now, we're going to extend this Pythagorean theorem idea in sort of 2 different ways, okay? One of those ways is going to be using the converse of the Pythagorean theorem. If you remember, converse means the theorem flipped around. So instead of saying if we have a right triangle, then the side lengths fit a squared plus b squared equals c squared, we flip that around. And we say if we can show that the side lengths of the triangle fit the Pythagorean theorem, then it must be a right triangle, all right? So basically, we're going to be given side lengths of a triangle, for example, 85, 84, and 13, and we're going to be asked to decide, is this triangle a right triangle or is it not, okay? So the only question here is, do these 3 side lengths fit the Pythagorean theorem? Now, one thing that we need to always keep in mind, the longest side of the triangle, okay, the longest side, no matter what order they give them to you, the longest side must always be the c value, okay? It has to be the c squared value. So the other 2 can be a and b in whatever order we want them to be. It doesn't matter the order. So I can go 84 squared plus 13 squared equals 85 squared, and I'm just checking to see, is this true? Is this true or is it not true? So if I do 84 squared, I get 7,056. If I do 13 squared, I get 169. When I do 85 squared, I get 7,225. So the question is, if I do 7,056 plus 169, what do I get? 7,056 plus 169. I get 7,225. Is that the same as 7,225? Yes. Okay, so we say yes. This is a right triangle. If these are the side lengths, it has to be a right triangle because those side lengths fit that Pythagorean theorem, okay? If they didn't fit, we just say no. It's not a right triangle, okay? Our explanation is this work here, or we can say, you know, because it fits the Pythagorean theorem, or because 13 squared plus 84 squared equals 85 squared, et cetera, okay? Also, let it be known, we've just also shown that 13, 84, and 85 are a Pythagorean triple, right? It's the same process to answer, is it a Pythagorean triple? Are these side lengths the side lengths of a right triangle, okay? Same process. Do they fit the Pythagorean theorem? Now, the other extension for us is what happens if it's not a right triangle? Okay, what if it isn't a right triangle? Well, then we end up with these two other theorems, which are sometimes called the Pythagorean inequalities. Okay, Pythagorean inequalities, and the reason they're called that is because it turns the Pythagorean theorem into an inequality with this greater than or less than symbol. Okay, and there are sort of two versions of this. What the Pythagorean inequalities say is if you do the a squared plus b squared stuff, and you do the c squared, okay, you take the side lengths and you do those things. C squared, of course, again, being the longest side. If the c squared value is bigger than the other two, then the triangle is obtuse, and obtuse means an angle bigger than 90 degrees, right? So if the c squared value is bigger than a squared plus b squared, then that angle is bigger than 90 degrees, and we have an obtuse triangle. If the c squared value is smaller than a squared plus b squared, if c squared is smaller, then the angle is smaller than 90 degrees, and we have an acute triangle, right? So this allows us to answer questions like this. Here's the three side lengths of a triangle. What do you know about the triangle's angle measures? Is it acute? Is it obtuse? Is it a right triangle, right? So in order to answer this question, we're going to focus in first on this longest side length, 14. We're going to do 14 squared, and that is 196, okay? Then I'm going to take the other two side lengths, in this case 6 and 11, and I'm going to square those and add them together, like I was doing a squared plus b squared equals c squared. So that ends up with 36 plus 121, which leaves me with 157, right? 157. So this number, how does it compare to 196? Or specifically, how does 196, the biggest one squared, compare to 157? Well, pretty obvious that 196 is bigger than 157. 196 bigger than 157. So this triangle is obtuse, because when the c squared value is bigger, the angle must be bigger than 90 degrees, which means obtuse, okay? So all of these sort of examples or applications of the Pythagorean theorem are in your practice problems. If you have any questions about any of them or how they fit into the Pythagorean theorem or anything like that, please reach out to me, let me know. Otherwise, that's all I have for you right now, and we'll talk to you soon.